let's look at this example here. So talking more about exponential growth and decay. And so what I would say is whenever someone says something is either growing exponentially or is decaying exponentially or is like basically is a radioactive substance, these are the things we typically talk about having exponential decay. You want to think about the fact that our model for exponential growth and decay is usually expressed as y equal to c e to the ket. There are lots of other ways of writing this using different letters for the constants, right? You might see it as like y equal to c e to the kx, or a equal p e to the rt, or any number of ways of writing the same darn thing 100 different ways. One more, you might see like m of t equal to m naught e to the kt. Whatever. These are all the same equation. I really want you to see that, right? Every one of these is the same. You have a constant times e to a different constant times your variable. Same thing, same thing, same thing. That's our model for exponential growth or decay. Then we need some sort of setup. So in this problem, here's the setup. Okay. TC99M, a radioactive isotope used widely in nuclear medicine, has a half-life of approximately 6 hours. We'll just say 6 hours. Suppose a patient is given a dose of 10 milligrams. How much will remain? How much TC99M will remain in the patient's body after, give ourselves a room here. Also, just in general, if there's something you can't see on the thing, please let me know. Or if you see that there's a chat that I'm missing out on, like if you see the little chat thing up there, you can all let me know. Hey, James, there's a chat, because I didn't see it until just now. We did this in Lee too. Oh, no, that's fine. Thanks. Appreciate it. Cool. So let's say the first question is, how much is there going to be after 24 hours? So actually, a nice thing about this specific question is we don't have to do any of the work to find the model, and here's why. Well, yeah, we're going to still. The amount of time that's going to pass is exactly a multiple of how long we were already given, right? We were given a 6-hour interval. Let's write down some data points here. So here's what I know so far. I'm going to have time, and I'm going to have the amount. So I know at the beginning, when I give the patient their dose of TC99M, which is time equal to 0, the amount of TC99M is going to be 10 milligrams. And then 6 hours later, how much is going to be in their body? You can show me on your fingers if you want. So just so everyone's clear, when we see something has a half-life of 6 hours or a half-life of however much time, what that means is it takes that much time for half of it to dissipate. Also, it takes that much time for half of it to still be left over. So in 6 hours, half of the TC99M will have disappeared and the other half will still remain. So after 6 hours, we're going to have 5 milligrams. After another 6 hours, so 12 hours after the initial dose, we're going to have half of what we started, or half of what we just had, which is going to be half of 5, which is 2.5 milligrams. After another 6 hours, so at hour 18, there's going to be half of 2.5, which is 1.25. And finally, after another 6 hours, we're gonna have half of that, which is 0.625. So we can see that from an initial dosage of 10 milligrams, 1 day later, we'll be left with 0.625 milligrams in the body. And that's wonderful if they ask you an exact multiple of whatever interval of time you have. But if I said, now I want to know how much TC99M is there going to be in the body after, say, 8 hours, well, with the things I've written down, all I can confidently say currently is there's going to be between 5 and 2.5 milligrams. I definitely know that there's less than 5 and there's more than 2.5, but that's really all I can say without doing more work. So this is where we have to actually start writing down the model. So here is our general model. And since I used A here, I'm going to write it as A, the amount of stuff I have at time t, instead of Y, equal to C e to the K times T. You might see people write it like this. You might also see people write it as A of T equals C e to the K T, just to kind of more strongly emphasize the functional relationship we have here, that the amount of stuff we have depends on what time it is. So we're going to use our data points. And so sometimes it won't be obvious what the data points are, but our initial data point is that at time 0, the amount is 10 milligrams. I'm going to take that and I'm going to plug it into my model. So the amount should be 10 and the time should be 0. I would say that you can usually bypass this step. If you know how much stuff you have at time 0, that's going to be the constant that you have out in front. When I solve here, I'm going to get 10 equal to C e to the K times 0 is 0, and e to the 0 is just 1. So C is equal to 10. And C, this constant out in front here, is always going to be the amount of stuff you have at the time equal to 0, or it's your initial time at the beginning. Sometimes you won't know that. Most of the time you will know that for these exponential growth and decay problems, but not always. But we still need to figure out what K is. So that's where we use our second data point. Now, reading the problem as written, they didn't actually give us the rest of these data points here. We came up with them. But if they tell you that the half-life is 6 hours, we are able to deduce that, oh yeah, 6 hours later, we're going to have 5 milligrams of stuff. So that's our second data point. So we're going to take that. We're going to plug it into our, well, I should have done one thing. So now our new updated model is A equal to 10 e to the KT. And then we're going to plug in this second data point to our updated model. So now the time is 6, the amount is 5. So 5 is the amount equals 10 e to the K times 6. And then we're going to solve for K. So I'm going to divide both sides by 10. Over here, so 5 divided by 10 equals e to the 6K. 5 over 10 is 1/2. Not surprising if we're using the half-life that we're getting e to the something equal to 1/2. That's pretty standard thing that happens. So I've got 1/2 equal to 6 e to the KT. I said something wrong there. I said 6 e to the KT. That's not right. E to the 6K. It's funny how you can look at something and think you're saying one thing and your mouth spits other words out. And then we're going to take the natural log of both sides. So the natural log of 1/2 is equal to the natural log of e to the 6K. I would recommend skipping writing this and just saying that we know that the natural log of e to the something is just going to be that something. So we actually have that the natural log of 1/2 is equal to 6K. Finally, solving for K, we get K equal to the natural log of 1/2 divided by 6. I would probably, oops, you can't quite see that, bless you. I would probably choose to leave it that way, but if you prefer, you could alternatively write this as the negative natural log of 2 divided by 6. I don't think you need to, but some people like to, when they have exponential decay, see that they have a K value that is negative. It's still negative either way you write it. The natural log of 1/2 is a negative number. The natural log of 2 is positive, so the negative natural log of 2 is negative. But either way you want to write it. And what I'm kind of using there, just so you all know, is I'm using the fact that the natural log of 1/2 is equal to the natural log of 1 minus the natural log of 2, right? Using the quotient rule for logarithms. And then the natural log of 1 is equal to 0. So that's just 0 minus the natural log of 2. That's the way I'm getting there. There's other ways to get there. That's the way I like to see it. So now we've got our fully fledged model that A is equal to 10e to the natural log of 1/2 over 6 times k times t. Oh my goodness. At least that time I said the wrong thing and wrote the wrong thing at the same time. This is not the only way to write this. In fact, it's probably worth mentioning, although I don't prefer it. I don't know. I don't think I have a strong preference. I would say in this class, we usually prefer to write it this way. But another way you could write this is as 10 times 1/2 to the t over 6. Which might seem like a leap. But let me show you where that's, well, I'll show you where that's coming from in a second. Well, let's talk about actually answering the question that we were asked. So now, to answer the question, how much TC99M after 8 hours, we're just going to set time equal to 8. So A of 8 is going to equal 10e to the natural log of 1/2 over 6 times 8. Which is about, I mean, you can simplify that a tiny bit, but without a calculator, there's really not much more you can do. Yeah. Say that one more time. Yeah. Is that visible? Good. Okay. Using a calculator, this is going to be approximately 3.97. So definitely, as expected, our answer is between 2.5 milligrams and 5 milligrams. But now we have a better idea that, okay, after 8 hours, it's pretty close to 4 milligrams still left in the body. Keep things in order, James. It's always a challenge to keep the papers in order over here. Trying to find a place to put them all. Sure, we'll go there. That might be. Just to kind of clarify, in case you're curious where this came from, there's a couple ways of seeing it. What I'm seeing here really, if I move my dumb picture out of the way for a second here. I guess it's not a picture, it's a video, whatever. Is that every 6 hours we have half as much as we had before. So look at this. If t equals 0, 1/2 to the 0 is 1, and 10 times 1 is 10. When t equals 0, we get 10. When t equals 6, 6 divided by 6 is 1. 1/2 to the first is 1/2. 10 times 1/2 is 5. When t equals 12, 12 divided by 6 is 2. 1/2 squared is 1/2 times 1/2, which is 1/4. 10 times 1/4 is 10 over 4, which is 2.5. So basically, if you know you're multiplying by 1/2 every time, then you can take 1/2 to the power, and the power has to essentially give you integers whenever you reach the next logical time interval. So every 6 hours needs to make our integer go up by 1. The more mathematical way of getting the more mathy way of getting there, instead of just like saying it makes sense, is actually taking this equation here. So note that you can take the equation a equal to 10e to the natural log of 1/2 divided by 6 times t, and you can make that into this by using some rules of logarithms. Check it out. I'm going to rewrite this as 10e to the t over 6 times the natural log of 1/2. And I'm going to use a rule of logarithms that says if you have a logarithm of something to a power, you can bring that power down in front. But we can also do the reverse. And if there's something down in front, we can bring it up as the power of the thing we're taking the logarithm of. So I can rewrite this as 10e to the natural log of 1/2 to the t over 6 power. And then, just like before, we have e to the natural log of some stuff. And the e to the something and the natural log of something, I don't want to say they cancel, I want to say they undo each other. E to the natural log of some stuff is just the stuff. So this is really 10 times just the stuff, which is 1/2 to the t over 6 power, which is exactly the thing we said it was up here, which again, I'm covering up with my video. Really, really good job there. Just right there. Right there. Same deal. Kind of neat. This is definitely how some books present it, more as like this instead of like this. I feel like this is kind of the more general way. This feels, I don't know, they're the same. I like this one better. Why? Because that's how I learned it 20 times and I never learned it this way. So, but if you like something, if you like this better, that's also fine. I will say, for me, it's easier to take the derivative of this. Whereas taking the derivative of this, you have to remember to like the end to like multiply by the natural log of your base. So, yeah. Yeah. Questions before I say questions. We're not quite. I'm gonna ask one more question actually, but let me ask you. Do you have any questions? Okay. Usually with these exponential growth and decay questions, so usually they kind of go this way. First, they give you some stuff, and you typically have to find the model. They won't say that all the time, but to answer whatever question they're asking you, like how much drug is in the system after 8 hours, you have to be able to find the model and then plug in 8 hours. And then after you found the model, usually you're either asked how much stuff is there at a certain time, or what time is it when there's a certain amount of stuff. So I've asked, the first question here was, how much stuff is there at a certain time, 8 hours, but we could also ask the other kind of question, like how long does it take until only 1% of the original dose remains in the body? Okay, so we're still going to use our model. One thing on our model is that the amount of stuff at time t was equal to 10 e to the natural log of 1/2 over 6 times t. And now we have to set the amount equal to the number that we need it to equal. So I'm not going to set it equal to 1, because 1 isn't 1% of what I started with. 1% of the initial 10 milligrams is how much? I know what percent personally. If I'm doing 1%, I'm really just dividing by 10 twice. So I'm really dividing by 100. 10 divided by 10 is 1. 1 divided by 10 is 0.1. So 1% of 10 milligrams is 0.1 milligrams. You could also divide by 100 or move the decimal over twice, whatever makes sense for you. For me, dividing by 10 twice, I don't know. It's honestly, that's how I multiply by 4 as well. I multiply by 2 twice because it's just easier for me to do it that way. So then we're going to set our amount, 10 e to the natural log of 1/2 over 6 times t, equal to 0.1. And then we're going to solve for t very similarly to how we solved for k previously, by first dividing by the coefficient out in front, and then taking the natural log of both sides, and then getting the thing we want by itself. So dividing both sides by 10, we have e to the natural log of 1/2 divided by 6 times t. That's all in the exponent, equal to 0.1 divided by 10. And 0.1 divided by 10 is equal to 0.01. Something worth noticing here is that whenever you're solving this kind of thing and you're trying to say that it's equal to some percentage of what you started with or half of what you started with, when you divide both sides by the coefficient, you're always going to get e to the something equal to whatever that fraction or percentage is. Just like in the beginning, we got e to the something equal to 1/2 after we divided both sides by 10. Here we're getting e to the something equal to 1% written as a decimal, which is 0.01. That is not a coincidence. That happens every time. And then we take the natural log of both sides. The natural log, I should have skipped this step and I'm writing it anyway. The natural log of e to the natural log of 1/2 divided by 6 times t, I'm writing too small, equals the natural log of 0.1. 0.01. Let me zoom in a bit so it's maybe easier for you all to see. Natural log of e to a thing is just a thing, so now I have the natural log of 1/2 divided by 6 times t equals the natural log of 0.01. By the way, in case you're curious, there's no rhyme or reason to why I sometimes write a 0 in front of the decimal and why sometimes I don't. I just do it sometimes. Like right here, I didn't write it. I wrote 0.01. I could have written 0.01. I just didn't. You don't need to ever write it, but sometimes I like to. I don't know why I don't do it sometimes, or I do it sometimes. It just happens. So there you go. Finally here, I would prefer to write my answer not as natural log of 0.01 divided by this whole mess here. I would multiply both sides by 6 and divide both sides by the natural log of 1/2. And then I would use a calculator to actually see what that's approximately, assuming I always feel like I brought my calculator and then I've always left it. Nope, I brought it. Okay. Maybe. Let's see here. So we've got the natural log of 0.01 divided by the natural log of 1/2, both of which are negative numbers, I'll just point out. And we get about 6.6, and then we multiply that by 6, and it's going to take about 39.8 hours. It's never a bad idea. Never is maybe too strong. It's usually not a bad idea to think about if your answer makes sense in the context of what you've already done. So I look back at the beginning and say, okay, well, I can see that after 24 hours, I was down to 0.625 milligrams, which is, well, 1% would be 0.1. So yeah, that seems reasonable. If I went another 6 hours, I'd be down to half of that, which would be 0.3125. If I went another 6 hours, I'd be down to half of that, which would be like 0. I don't know, 1.5 something. Right? Yeah. 36 hours, I'm down to like 0.15, and then another 6 hours, I'd be down to too little to be 1%. So yeah, 39.8 hours seems like a reasonable answer to this question. Cool. All right. So radioactive decay, exponential growth, they're not very exciting, at least from my perspective, because I've seen it many, many times. It will also probably be not very exciting to you because it's really the same stuff kind of every time. You're given a couple pieces of data, you have to figure out what the model is, then you're going to answer whatever question they ask by either plugging in the time and getting out a value for the amount of stuff you have, or plugging in the amount of stuff you have and then finding the time that happens at. That said, it's probably worth doing one more problem. It's good to practice this stuff because even though it's not exciting, it doesn't mean we don't need to practice doing it. You can't just do the fun math. Yeah, they're like, what do you mean? All right, well, let's look at one more example here. Yeah, sure, decay. So let's say we have carbon 14. I guess it's written this way. I don't know. I'm not a chemistry person. A radioactive element is used in carbon dating. Here's the carbon dating. And it has a half-life of 5,730 years. Again, all that means is it takes that long for half of what you originally started with to still remain. I always do like to phrase it as how much you still have left, because that's what the equation is actually telling you, is how much you still have, not how much you have lost. But people often phrase it as how long it takes for half of it to decay, and also by implication, how long it takes for half of it to be left. Suppose a piece of petrified wood Which, by the way, I remember it's really petrified wood's really neat. If you ever like checked out, like it's just cool. Like I remember we had like a piece of it when I was a kid that was like this big. It was just like that is a neat thing. I don't know. It was fun to hold and interact with. A piece of petrified wood has 15% of the carbon-14 of a living tree. Meaning, right, it's lost 85% of the carbon it would have initially had when it like became petrified. How old is this wood? So, notably here, they didn't give us any amounts of actual carbon. They didn't tell us at the beginning it had 1,000 grams of carbon, or at the time we found out it had 15 grams, right? We have no actual amounts, which is actually the best situation you can be in, even though it feels a little bit tenuous. You can make up whatever amount you want. So I'm going to say that the beginning, back when the tree had all of its carbon, I'm going to pretend like it was the easiest amount to deal with percentages with, which is 100. 100 watts doesn't really matter, but you can make up units if you want to. You could say 100 grams if you like, or you could say 1, or you could say C. Anything that works best for you. I like using 100 because it's nice and easy. And so I'm going to say over here, I'm going to say this is Y of T. I like using Y for the amount of stuff at time T. People like using A as well. Whatever you like. It does. You really use whatever you want. And then I know that, well, actually, what is my other data point? Some later time, I should be able to find some later amount. Why don't you try writing down what you think? Or thinking about another time and another amount. Both things we can fill in based on what we've written here. I'll tell you, it's not the 15%. There's some other amount of time and also unwritten amount of stuff we can fill in. I'll give you 30 seconds. No, just don't listen to me. My watch is trying to do things. By the way, there's a hint. Okay, so I've been almost 30 seconds, close enough. We know that 5,730 years later, we have half as much as we started with. We started with 100 grams or whatever number you wanted to say you started with. So now, this many years later, we have 50 grams. And then I also like to, in this little, whenever I'm doing exponential growth or decay, I always make this little table. I find it super useful. I also like to write in there the question, meaning they're asking me how long, so what time is it? We're trying to figure out what time it is when we get down to how many grams? 15, because 15 grams is 15% of 100 grams. That's why I chose 100, because it's easy to take percentages of. All right, so then we're going to do the usual things. We're going to use our data points, start with the model, figure out what C and K are, and then answer the question. So here's our usual model. Y equals C e to the kt. We know that C is going to be 100. I think you are perfectly fine to bypass saying that Y at time 0 is equal to 100, which is equal to C e to the k times 0. I think you can skip that and just say, yeah, I know that C is going to equal 100. And then we can go down to our new updated version of the model, which is Y equal to 100 e to the kt. And then we can plug in our other data point. We can plug in the fact that, when I say plug in the data point, I mean plug in a point where you know both the time and the amount value. That's what I'm referring to as a data point. So then I'm going to say that Y is what? 50. I ask because sometimes people accidentally get them switched and they want to say like the first thing there is the first thing. No, Y is, right? That's why I make columns with names. Y is 50, time is 5,730. You might have taken chemistry at some point in your life, and you might know that when you're dealing with half-life stuff, you always get essentially like that K is equal to the natural log of 1/2 divided by the half-life. You should still show the work. But if you know things, it's good to just be like, oh yeah, I have a good idea of what this is going to come out to be. 50 divided by 100 is 1/2. And it's equal to e to the K times 5,730. All right, I'm going to take the natural log of both sides, and I'm not going to show my work on the right-hand side. Taking the natural log of both sides, taking the natural log of 1/2 on the left, and the natural log of e to the stuff is just the stuff. K times 5,730. Finally, I'm going to solve for K and get K equal to the natural log of 1/2 divided by 5,730. So now we have all of the pieces we need for our new, our fully fledged model. Our model is y equal to 100 e to the natural log of 1/2 over 5,730 times t. And yes, let's zoom a bit. You can kind of look up there. I can totally look at my laptop right there or the screen right there. Start about this. Now what? I found the model. What do I need to do now to answer the question? Yeah. Well, not spelling water all over myself would be a good idea. Plugging 15 where? Right into y. So we're going to say that 15 equals 100 e to the natural log of 1/2 divided by 5,730 times t, and then we'll solve for t. It is essentially the same way we just solved for k. So divide both sides by 100, 15 divided by 100, again, not surprisingly, not coincidentally, is going to be 0.15 or 15% as a decimal. It's going to equal e to all that stuff, e to the natural log of 1/2 over 5,730 times t. Then we take the natural log of both sides, get the natural log of 0.15 on the left. The natural log of e to the stuff is just the stuff. So we get the natural log of 1/2 over 5,730 times t. Finally, multiply both sides by 5,730. Divide by the natural log of 1/2. And that is your time. And not that any of you are using WebWork, but if you were using WebWork, that's how you would write your answer in there. You wouldn't try to get a decimal approximation. But then if you wanted to actually have a more meaningful answer, because like, I don't know how long that is, I would use a calculator and I would get that the time is approximately 15,683 years. I like to think about if this makes sense. Well, I know that after 5,000, let's just say, let's round up to like 6,000. After 6,000 years, we're going to have about half of what we started with. After another 6,000 years, we'll have half of that, which is 25%. And after another 6,000 years, we'll have half of that, which is 12.5%. So 18,000 years approximately would get us down to 12.5%. So it seems reasonable that 15,000 years is getting us to not quite there. So yeah, our answer seems reasonable, which is good. I like to think about that. All right. Before we start talking about antiderivatives, is there anything else you would like to see me talk about when it comes to exponential growth, decay, or exponential functions, logarithm functions in general? We can backtrack and talk about derivatives if you want. Happy to cover other things. I just want to kind of see if there's anything people have questions about before we move on to like chapter 5. Yeah. So I don't know what he will make you do, but it's certainly plausible. Like it's not unreasonable to graph the exponential function. And that said, if I was going to graph this function, yeah, let's talk about that for a second. So let's say I wanted to graph the function, the model, y equal to, what did I have here? It was, where'd you go? 100 e to the natural log of 1/2 over 5,730 times t. So if I'm going to graph this, there's a couple things I'm going to focus in on. One thing is the y-intercept, which I already know, right? In fact, if I look back at my table for a second, I know that when time is 0, the y value is going to be 100. Yeah, that's kind of not true. That's kind of not true here because I made up the number 100, right? Like I chose 100 because we weren't actually given values. So what I'm graphing here is making kind of an assumption that, yeah, we actually did have 100 to start off with. But I guess we could change it and say, instead of having 100 to start off with, we have 100%. So we can make our y-axis the amount we have as a percentage if we wanted to kind of fix that. I'm not going to worry too much about that though, because it's not really that big a deal. So I know that on my y-axis, I'm going to have a y-intercept of 100%. We're starting at a t value of 0 and the y value of 100%. Do we have exponential growth or decay? Decay, right? It's radioactive. So we know that as time goes on, our graph should be increasing or decreasing? Decreasing. Now, another way of seeing that is by looking at the function here and observing whether or not the coefficient of your variable is positive or negative. If you have e to a positive number times t, it's going to get bigger as time goes on. If you have e to a negative number times t, it's going to get smaller as time goes on. The reason I point that is because it's not always super obvious that this number here is in fact negative. It is worth knowing that the natural log of 1/2, or more generally, the natural log of a number that's between 0 and 1 is going to be a negative number. So that natural log of 1/2 is negative. So this whole entire coefficient of your variable in the exponent is negative. So after I see that, I'm like, okay, great, it's decay, or I already knew it's decay. And then I'm really just going to draw the usual kind of exponential shape. That's kind of it. Yeah, you could plot some points if you wanted to, but they're really not going to make a difference. Like, if you really want to, you could be like, okay, I know that over here at time equal to 5,730 years, I'm going to have half as much as I started with. But I don't think you need to plot that point. I think if you're ever asked to graph either an exponential growth or decay kind of model, you really just have to have the right shape and maybe the y-intercept. And I guess also you should have the horizontal asymptote. I didn't draw it or write it because it's the x-axis, the t-axis, but we do have a horizontal asymptote at y equals 0. Because as time goes on and on and on, right, you keep decaying, but the radioactive material never fully dissipates. Again, we're not taking into account the fact that like splitting atoms, whatever. Like eventually, I guess the time went on long enough, yeah, you get down to 0 because if you have only one atom left, it's gonna eventually just kind of do whatever. I don't know. It's chemistry, magic. I don't know how it works. It's not the point. The point is we get closer and closer to 0 as time goes on. So yeah, you could be asked to graph it. If it was exponential growth instead, it would be increasing from left to right. For example, if we had bacteria that tripled every 4 hours, and we started with, say, 250 cells, we could find the model and graph it. Yeah, let's do that. Find the model for growth and graph it. Oh yeah, there's one more thing I should say. Let me ask a quick question. How many of you have to take 16C? A few of you. I'm going to say one thing that kind of pertains more to that class, but I think it's worth mentioning. So, usual deal. I'm making my chart. At time 0, how many bacteria do I have? And then at some later time, I should be able to find out an amount. I didn't explicitly say like 4 hours later, I have 700 bacteria. What I said was 4 hours later, or really what I said is that the bacteria triples every 4 hours. Is that a 4? Yeah, that's a 4, believe it or not. The bacteria triples every 4 hours. So I know that 4 hours later, I should have 3 times 250. And you could do more. You could say, and then 4 hours later, I should have 3 times 750. You don't really need to do more than that, but it's nice. It's not necessary. So then, usual steps for finding the model for growth. We start off with y equal to c e to kt. We plug in our initial thing. We know that this is just going to give us the coefficient out in front is 250. It's not whenever you're starting though, it's specifically at time equals 0. Like if they tell you, we know that 4 hours after the beginning you have some amount and like 10 hours after that you have some other amount, you can't be like 4 hours is your initial point, you have to kind of back it up in a weird way. So it really only works this way if you're given at time equals 0, you have this amount of stuff. So we know c equals 250, our updated model is y equal to 250 e to the kt. And then we're going to plug in this data point to figure out what k is. 750 equals 250 e to the k times 4. Divide both sides by 250. Not surprisingly, we get 3 equal to e to the stuff. And then we're going to get the natural log of 3 equals 4 times k. And then the natural log of 3 divided by 4 is equal to our k value, also called the relative growth rate. And then we can write the model. Our model is y equal to 250 e to the natural log of 3 over 4 times t. And then we can graph it. I know that at time equals 0, my population, my number of bacterial cells is 250. If you really wanted, you could plot another point. You could say, I know that at time equals 4, my population is tripled. Try to make it not too terrible to have to actually graph it. But really, I'm just going to, I wouldn't plot that point, to be perfectly honest. That's not my style. I would say, great, I've got my y-intercept. I know it's increasing from left to right because it's exponential growth, or because my k value here is positive. The natural log of 3 is definitely a positive number. And so this is going to look like your usual exponential shape, increasing from left to right. That's it. That's all I would do to graph it.
When we're graphing it, do we have to extend it beyond the y-axis? Because we can't have a negative value for t, yeah?
Well, that's an excellent, you make a good point. Yeah, so I'm graphing the whole function just because that's what I'm used to doing, but you're right, it doesn't really make sense to think about the domain here, wouldn't really include t being negative. So a better actual graph here would just be to start at t equals 0, be like, oh yeah, we kind of like, we have the ghost of the graph there, and then we're really just getting this part up here. Yeah, I like your point. It's a good point. Right, if the domain, if t being negative doesn't make sense, and it usually doesn't make sense to think about time being negative, then yeah, we shouldn't include that part of the graph. Even though it's part of the explicit domain of the function, right? That function, if you're not thinking about what makes sense, would have a normal domain of everything from negative infinity to positive infinity. But the implicit domain, where we're thinking about like in the context of the problem, what actually makes sense for the domain, oh yeah, time should be non-negative. So yeah, good point. Yeah. Yeah. And I would say that's probably actually fairly generally true for these problems, because most of the time we're thinking about something being a function of time. Yeah.
What did it say after the 4 hours in the original?
Good question, because my writing was not the best there. It says bacteria that triples every 4 hours, and we started with 250 cells. Yeah, I might have been writing a little faster than I'm able to there. Find the model for growth and graph it. And then if you wanted to, we could answer questions about like, how long does it take until there's 1,000 cells, or after 24 hours, how many cells will there be? But I think we've done enough of that. So are there other, actually, there's one other thing I want to say here, just because I want to talk about how I'm thinking about this. So whenever I'm thinking about the natural log, like, is it positive or negative? I'm really just imagining the graph of the natural log of x. And we know that this intercept is the point 1,0. So notably, if your x value is larger than 1, so if you're over here, where x is larger than 1, your corresponding y values are positive. Whereas if you're in here, where x is between 0 and 1, then your corresponding y values are negative. So that's why when you take the natural log of something bigger than 1, it's going to be positive. Whereas the natural log of some number that is between 0 and 1 is going to be negative. That's how I knew that the natural log of 1/2 was negative. That's how I knew that the natural log of 3 was positive. I'm just thinking about what this graph looks like. Also, did I say the thing about your right hand before? I feel like I did. No, maybe it's not. I think not everyone was here for that. Just as a reminder to everybody, your right hand is probably a little bit easier to see it on. If you look at your right hand, you might have this line right here, this curve, which kind of looks like e to the x, and this lower curve over your thumb pad thing, whatever, that kind of looks like the natural log of x. Make sure you're looking at your right hand, right? If you look at your left hand, it's different. Your left hand has like e to the negative x and the natural log of negative x. If you look at your right hand, you kind of have those nice natural graphs on there, I think. Cool. Moving on. Chapter 5.1. Antiderivatives. So we essentially now have learned all of the derivatives we will ever learn in this class. The derivatives of x to a power, the derivative of trig functions, the derivative of the natural log function, the derivative of the exponential function. That's kind of the whole list. And yes, there are always chain rule versions of any of those things, but that's just a rule. Well, now we're going to try and undo those things. So instead of asking what's the derivative of this function, we're really going to ask, the way I would ask is, what's the function that we would take the derivative of to get the function we're asking about? Here's what I mean. Here's some notation. Yeah, I'm just going to start off with that. So this is typical notation for the antiderivative of something. That's also referred to as the integral symbol. And there's a nice kind of relationship between integrals and antiderivatives. But for now, when you see this symbol, I just want you to think, oh, we're taking the antiderivative. So the antiderivative of x to the fourth with respect to x, this is the antiderivative of f of x equal to x to the fourth. Or in other words, what this means is we are looking for the function, and just to introduce a little bit more notation here, typically if we call the function, the original function, little f of x, we often denote its antiderivative as capital F of x. That's a pretty standard thing people do. So we are looking for the function, I'm going to call it capital F of x, that if we take the derivative of f of x, which we would write as f prime of x, we end up getting x to the fourth. That's the whole idea. If you're trying to find the antiderivative of x to the fourth, we are looking for the function that if we take the derivative of it, we get x to the fourth. So we're kind of going to be undoing the power rule here, right? I know that the derivative of x to the fifth is 5x to the fourth. I don't really want that 5 though. So I think the answer that I actually want is that the antiderivative of x to the fourth is 1/5 times x to the fifth. Because if we take the derivative of that, and leave yourself a little room to the right there, because I'm gonna fill something in a second here. Because the derivative of 1/5 times x to the fifth is 1/5 times 5x to the fourth, which is in fact x to the fourth. Or in other words, derivatives and antiderivatives undo each other. If you take the antiderivative of the function and then take the derivative of that thing you just took the antiderivative of, you get back to where you started. It is not that dissimilar from inverse functions, except instead of being inverse functions, they're inverse operations. They're inverse things that we're doing. You're taking a function, you're changing it into another function by doing a thing to it, and then you're changing it back into the function you started with by doing the reverse thing to it. So really, 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 derivatives and antiderivatives undo each other, which is how you know if you've done it right or not, assuming that you're good at taking derivatives. So the one thing I have to add on here is plus a constant. Because technically, the antiderivative of x to the fourth could be 1/5 x to the fifth plus 0, or it could be 1/5 x to the fifth plus 7, or plus 9, or plus 1,000,000,000, or plus pi, or plus any constant you like. So when we write it this way, we were saying this is the most general antiderivative of f of x equal to x to the fourth. And notably, if I added in the constant down here, what's the derivative of a constant? Right, that's why it doesn't matter really. If I add in a plus c here, then the derivative of that plus c is going to be plus 0, which isn't going to make a difference. Okay, so antiderivatives are undoing the things we've done before. Let's look at a few examples. Oh, and actually, let's actually, why don't you all try this one? I'll try to use some numbers here. We'll see how long that lasts. Try finding the antiderivative of x to the seventh. It's going to be very similar to what we just did. Maybe you'd like to see the things I'm writing. Maybe. So I would prefer to think of this as 1/8 times x to the 8th, but I'm probably going to write it as x to the 8th divided by 8 plus a constant. I like writing it like this because it takes a little less room, but if I was going to go back and take the derivative, I would not like to write it like this, because if I write it like this, it makes me feel like I should be using the quotient rule. And although you could, you really don't need to, because I should really be thinking of this as the derivative of the constant 1/8 times the function x to the 8th plus whatever constant c. And then when we have a constant times a function, the derivative is just that constant times the derivative of that function. And then the derivative of a constant on its own is just 0. So we do end up getting back to where we started, as we should. We don't have to do this work of checking, right? If you are confident that you did the right thing in the first place, you don't have to go take the derivative of it to make sure that you got back to where you started. Excuse me. But in the beginning, it's a good idea to be like, oh yeah, the thing we're doing actually is the right thing, because if we take the derivative, we do get back to where we started. So generally, we have what I like to call the anti-power rule, or the reverse power rule. I like anti-power rule, but I think so. Is that the antiderivative of x to some power is, well, in each case so far, we've added 1 to the power. and then divided by the new power. And then we tacked on a constant. Which really is you're undoing the thing you did by doing the opposite things in the opposite order. So for the power rule, I'll just remind you, for the power rule, the derivative of x to a power is that power times x to the power minus 1. So first you multiply by the power, then you subtract 1 from the power. Whereas when you do the anti-power rule, you do the opposite things. So instead of subtracting 1, you add 1. Instead of multiplying by, you divide by, but you do them in the opposite order. So first you add 1 to the power, then you divide by the new power. Opposite things in the opposite order. Kind of cool. That's kind of how inverse functions work as well. There's one thing I failed to say here. This rule, there's one value, there's one power it doesn't work for. What value of p would be problematic in this expression over here? If I'm dividing by p plus 1, right, I don't want to divide by 0, meaning I don't want p to equal -1. So we have to exclude from our list here, p can't equal -1. And we'll come back around to that in a little bit. Let's do it right now. Yeah. So we might as well. So what's the antiderivative of x to the -1? I don't love writing it that way. Usually I do. Usually a negative power, I'm perfectly fine with writing. But this one in particular, I feel like it makes a little bit more sense, or it's easier to see if you rewrite x to the negative first as 1 over x. Who can think of a function whose derivative is equal to 1 over x? The answer should be all of you. What's the function? The natural log of x. Now, although that answer is mostly right, it's actually not the rightest it could be. So we need to fix this. Here's the real issue. It's kind of a subtle thing, but we're going to talk about it anyway. Typically, when you find the antiderivative of something, you should be able to differentiate it and get back to there. But the problem is there's a domain issue. The function 1 over x is defined everywhere except for at 0. It's defined when x is negative and when x is positive. Draw some pictures. So y equals 1 over x. Looks like this lovely graph. Everyone's favorite hyperbola. On the other hand, the derivative of this equal to the natural log of x is only defined when x is greater than 0. Normally, that's not a problem. Say, if you start with this and you take the derivative, it's perfectly fine for the domain to get smaller when you take a derivative of something. On the other hand, if you start with this, you take the antiderivative, it's problematic if the domain is getting, sorry, I said the wrong thing. Apologies. If you take the antiderivative of this, and the domain gets smaller, that's kind of funky. I think I said the wrong thing before. I'm sorry. The derivative of the natural log, yeah. Oh, I did say the right thing, but I said the wrong thing. So what I said was, when you take a derivative, it's okay for the domain to get smaller. That's not what's happening here. The domain here is only positive values, and its derivative has a larger domain. So let me say more. And again, you might not need to write this down, want to write this down. But here's what I'm pointing out. Oh yeah, I did. Yeah, I wrote terrible things. Can anyone tell me the terrible things I've written? The lies I have written on this page? Well, here's the mistake I made. The lie I told you. I wrote that the function was 1 over x and the derivative was the natural log of x. But what's the derivative of the natural log of x? 1 over x. So let's just pretend like that never happened. Fix it. So here's what I should have been writing. Apologies. The function natural log of x looks like this. And when you take the derivative of a function, the derivative can only exist where the function already exists. To be differentiable, a function has to have been continuous in the first place. To be continuous, a function has to have been defined in the first place. So if you're starting with the natural log of x, the derivative is, what's the derivative, everybody? I make sure I get it right too. Just a reminder, I do occasionally make mistakes. Please point them out. I don't intend to, usually. If I do intend to, you'll see me like muggy, like did I do something wrong, right? Like, but if I actually just made a mistake and I don't see it, please say something. The derivative here is only defined on the domain of the original function. So here, dy dx is 1 over x, but only when x is greater than 0. So my derivative looks like this. So the problem that we're encountering with the other thing is that if we start off with 1 over x as our entire function, which is this entire thing here, we really need the antiderivative to have as much domain as the function we're starting with, so that when we take the derivative, there isn't some weird domain issue. So here's how we fix it. The antiderivative of 1 over x isn't just the natural log of x, it's the natural log of the absolute value of x. Plus c, I don't really want to draw the plus c part, so I'll leave that for the next one. Here's what this looks like graphically. It looks like regular old natural log of x when x is positive. And then it looks like you took that and mirror imaged it. So it looks the same on the left. It looks like a reflection. I'm never good at drawing. Yeah, this should look like a mirror image. Oh, wow, that's not my best effort ever, but you can imagine it looks like a mirror image. Ooh, can you? Maybe. You can try. Those should be reflective of each other. If you graph it, in fact, why don't we use the tools we have available to us? Just so you all can see it looking nice. I don't want all that, though. I don't want that either. Come on, Desmos. Give me the graphing. There we go. Cool. So, so just to point out, what is going on? I don't want any of you. Please stop being so annoying. Y equal to the natural log of the absolute value of x. Of course. Why don't you just give me? Sometimes computers are not my friend. Yeah, that's good. There we go. There we go. Here's the nice function I was actually trying to draw for you. Maybe, not ever. What's your problem? Can I not just throw in an absolute value symbol there? Fine, gotta do it that way. No, okay, fine. I can't do it. I can't make it happen. Sorry, I'll just have to deal with my terrible graph. Yeah, I don't love that. You shouldn't need the parentheses though. Well, anyway, there's your lovely natural log of absolute. So importantly, when you find the antiderivative of 1 over x, it really is all of the natural log of the absolute value of x. It is incorrect to not write the absolute value. So why is that true? Well, what's the derivative of the natural log of the absolute value of x? So whenever you're differentiating a function with an absolute value, you have to kind of think of it as being piecewise. Yeah. So I'm going to write this as the derivative of, all right, so absolute value. Absolute value. The absolute value of a positive number is just that positive number. So if x is already positive, then the natural log of the absolute value of x is just the natural log of x. Joy of joys. On the other hand, if x happens to be negative, the way you turn a negative number into a positive number is by multiplying it by -1. So the absolute value of x is going to be -1 times x. If x is -5, the absolute value of -5 is -1 times -5, which is +5. And the natural log of that is the natural log of 5, which is totally fine. I can talk more about this if people want me to, if it's unclear what's happening there. But it's really because, right, if you look at the absolute value function, you get y equal to x on the left and y equal to -x on the left. I said y equal to x on the right, y equal to -x on the left. That's why we're breaking it up this way. And now check this out. If we take the derivative of the natural log of x, we get 1 over x when x is positive. And if we take the derivative of the natural log of -x, okay, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff when x is negative. But look, those are the same. 1 over -x times -1 is 1 over x. So either way we slice it, we get 1 over x as long as x is not 0. So it really is the case that since the derivative of the natural log of the absolute value of x is equal to 1 over x, then it is true that the integral, or I should say antiderivative of 1 over x is the natural log of the absolute value of x. And then we can tack on a plus. Great. So now we know how to anti-differentiate any power of x. Let's look at some examples in the last 8 minutes here. So let's say we want to find the antiderivative of the following: x to the 9th plus the square root of x plus 1 over x cubed plus 7. And before I do this, I would rewrite it so everything looks just like x to a power. So I would rewrite this as the antiderivative of x to the 9th plus x to the 1/2 plus x to the -3 plus 7. If you really wanted to, you could write 7 times x to the 0. I don't think we need to write that. So now we're going to anti-differentiate, which is what this symbol is telling us to do, right? This symbol here, this curly looking thing and this dx, those are just instructions telling us to find the antiderivative. And now we're going to follow the instructions so we no longer need to write them. The antiderivative of x to the 9th is x to the 10th divided by 10. The antiderivative of x to the 1/2 is x to the 1/2 plus 1 divided by 1/2 plus 1. The antiderivative of x to the -3 is x to the -3 plus 1 divided by -3 plus 1. And the antiderivative of 7, the derivative of a constant is 0. The antiderivative of a constant is that constant times x. Because the derivative of 7x is 7. And then finally, we need a plus c. I would choose to simplify this a bit. I would write this as x to the 10th over 10. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. And I don't typically prefer to divide by a fraction. Instead of dividing by 3/2, I would prefer to multiply by 2/3. Same deal. No, not the same deal. This is going to be x to the -2 divided by -2. I would probably write this as minus x to the -2 over +2. We don't usually like to write division by a negative. We'd rather write minus division by a positive. And then finally, plus 7x plus c. Something I want to point out that we all just did without even thinking about it was we said that the antiderivative of all of these functions added together is just all of the antiderivatives added together. So whenever you have an antiderivative of a bunch of things either added or subtracted together, you can do each one and then add or subtract the results together. Let's do another one. So we want to find, oh yeah, we'll make this one. Sure. The antiderivative of 5x to the 7th plus 3 cosine of x plus e to the x minus secant of x times tangent of x. All right. I don't think we need to do any rewriting because all of our powers are already written as x to a power, not something like 1 over x to the something. So not all these are powers though, right? These are other functions that look like derivatives of things I know. We'll start off with the first one though. So the antiderivative of 5 times x to the 7th is going to be 5 times the antiderivative of x to the 7th, which is x to the 8th over 8. All right. The 3 hangs out. Just like with derivatives, constant multiples hang out for antiderivatives as well. So if you have a constant times a function, you're taking the derivative. Constant, if you have a constant times a function, you're taking the antiderivative, the constant just hangs out. So what's the antiderivative of cosine of x? Right, and it is positive sine of x because the derivative of sine of x is cosine of x. If I was asking for the antiderivative of sine, it would be negative cosine because the derivative of negative cosine is negative sine, which is sine. The antiderivative to the x is e to the x. And the antiderivative of secant of x times tangent of x. So all we're doing is we're trying to think of what function can I take the derivative of and get secant of x times tangent of x. Is it tangent or is it secant? It's definitely secant. The derivative of secant of x is secant of x times tangent of x. So the antiderivative of secant of x times tangent of x is just secant of x. And then I might prefer to write this as 5/8 times x to the 8th, but I'm not going to rewrite the whole thing just for that one minor change. So I would leave it like that. I will point out, this is why it's fairly important to be pretty comfortable knowing all the derivatives of the 6 trig functions, because you have to be able to look and see, oh, is that a derivative of a known trig function? Let's look at, we got time for one more. Yeah, we got time. Maybe even, yeah, sure. Let's say we want to find the antiderivative of x to the 5th plus 2x cubed plus 7x over x squared plus secant squared of x. You might like to see that. So the bad news, it's maybe not bad news. The news is that there is no anti-quotient rule. You can't look at a quotient and be like, oh, just apply some. And that's kind of generally true. Unlike differentiation, where we have kind of like just set rules, like you see a product, you use the product rule. You see a quotient, you use the quotient rule. You see something that needs the chain rule, you use the chain rule. For anti-differentiation, half the battle or more is figuring out what method to apply to even start trying to anti-differentiate it. Here, and generally, simplifying an expression is almost always a good thing to do. So since I have a quotient where the denominator is a single term, I can rewrite this as each of the things in the numerator divided by the denominator. So x to the 5th divided by x squared, 2x cubed divided by x squared, plus 7x divided by x squared. And I still have the secant squared of x over here. And then I can do the division. X to the 5th divided by x squared is x cubed. 2x cubed divided by x squared is 2x. 7x divided by x squared is 7 over x. I'm gonna write it as 7 times 1 over x. Plus secant squared of x. And then let's cut to the chase since it's 1150. That's gonna be x to the 4th over 4. Plus 2x squared over 2, is just going to be x squared. Plus 7 times the natural log of the absolute value of x. Plus the antiderivative of secant squared is tangent of x, because the derivative of tangent of x is secant squared of x. Plus c. So if you have a rational expression like this, and the denominator has a single term, it is often the right thing to divide each thing in the numerator by that single term. So then you have just a bunch of powers of x to deal with. All right, I'll see you all on Tuesday.